Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. Hi, that is we here, and this is for the EPF3108 mass and energy balance. In the previous lecture, I already show you how to do some solution of the material balance when it comes to the single process, and today we are going to proceed by solving material balance problem when it comes to multiple processes without any chemical reactions. Multiple unit system represent the real complex industrial processes, because industry is involved so many processes, not only one process, normally expressed by process flow diagram or block diagram. So process flow diagram is like this. This is the process flow diagram of ammonia plant, where the feed from here will go to a few processes in order to produce the ammonia here, and this based on the diagram. So this is what we call as the process flow diagram. However, in the same time, it can also be represented by the block diagram. Okay, so because it's block, so all the processes involved will be in blocks, like what we have done in the previous example of the mass balance. And this is one of the way to do to represent the processes involved. And in order for us to simplify things, most of the time we just draw the block diagram because it's more convenient for us. And you can see here the ammonia plant consisted of so many processes, not only one processes, and we need to ensure that the mass balance or the material balance from one process to another will be balanced, and also the overall balance from the feed to become the product will need to also be balanced, and that's what we are going to do today. So strategies to solve the multiple processes, more or less is the same as the single process, where there are 10 strategies to do it. Similar strategies if you were to compare with the previous lecture. However, I want to highlight here at the second step, which is to draw the process and specify the system boundary. So what does it mean by the system boundary? I'm going to show you later in the example. Let's start by doing example 10.1, mixer and separator. A feed containing equimolar, that means that it have a equal amount, yeah, equal amount of amounts of water and methanols is mixed with 10 kg per hour of aqueous stream. So aqueous stream containing 40% of methanol. The mixture enters a separation unit that creates two streams. The top exit stream contains 70% methanol, while the rest is water. The other stream, which is 70 kg per hour, enters a second separation unit. The top exit stream of the second unit contains 50% methanol and 50% of water. The other stream is unknown. If the fresh feed to the system is 100 kg per hour, this is the equimolar mixture, the first sentence here, and the two top stream have the same flow rate. Find the flow rate of the other stream exiting the second separation unit. Okay, so based on this question, you can see there are a few processes involved. The first one is the mixing process, and then it goes to the separation process, and then this is separation 1, and then it also have another separation process, separation 2. So all of this information we need to take note, and extract in order for us to draw the block diagram. The second, the similar step like what had been listed in the previous slide, step 1, 2, 3 and 4, a flow diagram need to be drawn. Determine process unit involved. In this case, mixing, separation 1 and separation 2. So we have 3 processes. And also it's very important for us to determine stream in and out, how many that go in and how many that go out. Label the quantities, which one the fraction of the compound that we know, which one the flow rate that we know, and which one that we don't know. And then after that, the steps 5, 6 and 7 is to determine the degree of freedom analysis. And the degree of freedom analysis is more crucial to be performed for the multiple processes, because you want to know where should we start from. And the degree of freedom analysis can be performed on the overall and on each process. This is each process. OON. Sometimes we have to do to all the processes and the overall. And step 8 until 10 is to solve the balance, and this is similar like the previous lecture where I show you how to solve the balance of any particular single process. Okay, so based on the information given in example 10.1, we came out with this block diagram. You know, the mixing, the feed, this is feed, it's containing 100 kg, the flow rate is 100 kg per hour, and because it is equimolar, that means that it have 50% of both component. See again, equimole of water and methanol. Okay, and then another stream that go into, we have 10 kg per hour, and it's consisted of 40% of methanol and 60% of water, and this will be mixed in the mixing process before we can go to the separation one. So from the mixing process to separation one, the separator one, we have another stream. We just call it as N1, and we have no idea what is the fraction of the methanol as well as the water. So we just put it Y1M, which is represent methanol here, and for water it's just 1 minus Y1 minus Y1. This is for water, but because we just want to simplify it, we just focus on the methanol. Okay, because this is only consisted of 2 components, which is water and methanol. Okay, and then from the separation, it's produced 2 stream. One stream, the top stream, we consider as N2. No information about the flow rate, but we know that the fraction of methanol is 0.7 and the fraction of water is 0.3. And then the bottom stream will go to separator 2, and we know the flow rate of the the bottom stream is 70 per kg per hour, but we have no idea what is the fraction of methanol. And then the separator 2, the top stream contain 50% of methanol and 50% of water, while the bottom one, we have no idea about the flow rate, but we also have no idea about the fraction of methanol. And in the same time, the question also give one equation, N2 equals to N4. The top stream of both separator has the same flow rate. So this is an equation that we need to also bear in mind. So the question asks us find the flow rate of the other stream exiting the second separation unit. Okay, so the question asks us what is N5. Okay, so this is all the information given that we can do in order to solve the problem. So after we draw this diagram, what we can do now is to do the degree of freedom analysis. Okay, for this, let me change to other color. Maybe I change to red here. Okay, so for the degree of freedom analysis, for this one, it can be done for for the specific process. For instance, like this one. So I just going to put red as the process boundary. This is the process boundary for mixing. So we just going to consider what go in, which is this and what go out. We don't consider about other process. And then we have another boundary, which is the separator one, in which we just going to see what go in the separation one and what go out, which is this part, and for separator 2 also. So these three processes need to be performed with DOF. In the same time, we also need to perform the overall DOF. What does it mean by the overall process DOF? Overall means that we kind of like widen the boundary of the system so that we consider all these three processes is one process. So okay, so it's going to be like this. Just going to highlight it. Okay, so if you consider the overall DOF, that's mean that what go in, this is what go in 1 and 2, and what go out, this is 1 that go out, 2, and then 3. So we have 2 stream that go in, and we have another 3 stream that go out, and we don't consider other stream that involved in the process like this. So this is very important for you to determine what is the boundary of the system that you want to do in order for you to calculate the DOF. If you got this, then you will be able to answer the DOF analysis. Okay, so I'm just going to erase back, and then we can go one by one, imagining that we are going to do the DOF. Okay, I'm just going to do it here. DOF. Okay, one is for the overall, another one is for the mixing, separator 1, separation 1, separation 2. Okay, so in order for us to calculate DOF is equals to the unknown minus the components minus equation. Okay, so just going to list out here unknown, the components and equation. So let's let's just go one by one. Okay, for overall, imagine back, for overall, what that go in is this one, and go out this one, and also this one. We don't consider N1 and this 70 kg because this is part of the inside of the system. It don't go out or go in. So for overall, how many unknown here? We have N2, 1, N4, N5, and Y5. So I'm just going to list it here. N2, N4, N5, and Y5. So we have 4 unknown. Okay, for the component, how many component that we have? We have methanol and water. So we have 2 minus 2. Do we have other equation? Yes, we have one equation here. N2 equals to N4. So this is another minus 1. So the overall DOF is equals to 1. So we cannot perform the overall mass balance. So we go to the second, the first process. Now we are focusing on the mixing process. What go in? 1, 2, and what go out? This one. Yeah. So for mixing, how many unknown? We have N1 and Y1. N1, Y1. So we have 2 unknown. How many component? We have methanol and water. So we have 2 component. And then is there any equation? No, we don't have any equation. So after deducting 2 minus 2, we have 0. So for mixing, the DOF is 0. So that means we can solve the equation, the mass balance in the mixing process. Okay, let's go to the separation one. How many unknown? We have N1, we have Y1, we have N2 here, and also we have Y3. So in total we have 4 unknown. How many species? Again, we have the methanol and water, so minus 2. Is there any other equation? No. 0. So after the 4 minus 2, we have 2. So we cannot solve the mass balance in separation 1. What about separation 2? How many unknown? We have Y3, we have N4, N5, and Y5. So we have 4. And the amount of component, we have methanol and water, which is 2 minus 2, and we don't have any other equation. So here also we got 2 DOF. Again, I want to highlight that the equation here is only valid for overall, because this only the situation where this stream and this stream are involved. In other situations, such as in separation 1, only this N2 stream involved but not N4. But in separation 2, only N4 involved but not stream of N2. That means that this equation cannot be applied in separation 1 and separation 2. It can be only applied in the overall mass overall process. Okay, so based on the DOF here, we need to decide from where we should start solving the mass balance. And based on the DOF, we found that at mixing process the DOF is 0, so we should start by solving the mass balance in mixing process first before we can get more information and more data and about N1 and so on, so that we can solve other processes as well. So we need to start from mixing. So let's just start with the mixing process. Okay, so here is for mixing. So for mixing process is we have the general balance or the overall balance, as well as the component balance. For component, we should so we start with the general balance first. Okay, so general balance is 100 plus 10 equals to N1. 100 plus 10 is equal to N1. So with this we can solve N1 equals to 110. So what is the unit here? Is kg per hour. Don't forget about the unit. When you do the final answer, please include the unit as well. And there is possibility that I want you to change. Although you already got the unit in kg per hour, maybe the question will ask you to change from kg per hour to maybe pound per second, let's say. So after you got the final answer, you still need to do the unit conversion from here. Yeah, but this one the question doesn't ask about the unit conversion, so just fix with this. Okay, and then we have the methanol balance. It is the general balance or the overall balance, and then we have the M balance. For M balance is 100 times 0.5, 10 times 0.4, and 110. So we already have this 110 times y1. Okay, so 0.5 times 100 plus 0.4 times 10 equals to y1. Okay, now we are going to find y1, 110, because we already have n1 here. So y1, after do the arrangement, we're going to get y1 equals to 0.49. Okay, so we already got here 0.49. Okay, so now we can move to by considering this, we can do another we can guess where after this where to do the based on the information that we already obtained here, we can decide where to continue with the mass balance, because we already have N1 and y1 here. So in separation 1, N1 and y1 already been solved, so the unknown is now is only 2 minus 2, and now separation 1 also can be solved. Okay, so now we are going to move to the mass balance of separation 1 by considering that DOF now has been can be 0. So now we are moving to the separation 1. 1. Okay, so for separation 1 also, what we can do is to do the general balance or the overall balance. It's, well, actually you can use a different term for it as long as people can understand it. For the general balance for it, we can go back here. We have 101 equals to N2 plus 70. 110 equals to N2 plus 70. So we can get N2 equals to 40 moles, 40 kg per hour, sorry. So this is the answer for N2. Okay, now we do the M balance. Okay, we have 0.49 times 110, and this one you already got 40, and 0.7 can times this, and then 70 will times y3. Zero 0.49 times 110 equals to 0.7 times 40 plus y3 times 70. So after do the calculation, y3 will equals to 0.37. Okay, so this is a fraction of y3 here. 0.37. Okay, and also based on the information here, we know that N2 is equals to N4. So N2 is equals to N4, N2 is 40, so N4 is also 40. So now we want to see whether what is the next step, whether we need we can do the mass balance at separation 2 or the overall. Well, here we have, if you can see here, and y3 soft and 4 soft. We can also do the separation in we can also we can do the mass balance in the separation 2 here, by considering that we already got the the remaining unknown is only 2, and we have 2, so this one is 0. But in the same time, we also can do the overall balance too. We can see we have the N2 already, and N4, and don't have N5 and Y. Okay, this is also 2. So now the next step, we can either choose to do the general overall mass balance, or we can focus on separation 2, because at the end the aim is to know what is Y5. Yeah, so for this I want to do the overall mass balance instead of separator 2, but you can do separation 2 mass balance if you want, by considering the DOF is also 0. But here I want to show you the mass balance of the overall to get Y5. Okay, for overall mass balance, so we go to this. This is overall. So for overall, the general balance, because I use the term overall here, so that's why the balance here I use general balance, will be, okay, what go in 100 times 0.5, 10 times 0.4, and then the stream that go out equals to 0.7 times 40, 0.5 times 40, and then N and Y5. So For the for the general balance, we have 100 plus 10 equals to 40 plus 40 plus N5. So we're going to get N5 equals to 30 kg per hour. So now we go to the M balance. Okay, so we go to the M balance, the methanol balance. Zero 0.5 times 100 plus 0.4 times 10 equals to 0.7 times 40 plus 0.5 times 40, and lastly y 5 times 30. So at the end we are going to get y5 equals to 0.2. Okay, so this is the final answer, where the question asks what is the fraction of methanol in the second separation bottom stream. So this is the final answer. However, when and in the same time, I again for the third step, this is step one. We need to start with mixing, and step 2, and then for step 3, by considering the DOF for the overall, and for the separation 2 is already 0, you can choose whether to do the overall balance or maybe you can do the separation 2 balance. It's up to you. You can still got the same answer at the end. Separation 2 balance, you will get same y5 equal to 0.2. And again, for the calculation of the multiple processes like this one, the step is very important, because I want to know all the value, because although the question only asks what is y5, however, in order for us to get y5, we need to know the value of n1, y1, n2, y3, and n5. Because after we got all the information, then we can get the value of y5. So all these can be all these will be given marks in the examination and in the test. And yeah, so that's the example of multiple processes, a bit longer than the single processes. However, the way to solve the balance is similar like the single process. You have the general balance, you have the component balance. The component balance can be either, in this case, methanol, or you can also go for the water. But since the question asks about methanol, so we just go for ethanol. So again, this is the way to do it. We need to follow the step and do the calculation step by step to get the final answer. Okay, so now we go to the second example. This is for the extraction and distillation. Example 10.2. In a two-stage process, acetic acid A is extracted from water in hexanol in a liquid extraction vessel. Okay, so we have three components here. One is A, acetic acid, one is water, and also hexanol, H, in a liquid extraction vessel, and the extract is subsequently separated by a distillation. Assume the water is completely insoluble to hexanol. A mixture of 18% of acetic acid and the balanced water is fed to the liquid extraction. So this is the feed, where it consists of 18% of acetic water and the remaining is water and acetic acid, and the remaining is water. Feed in the extraction process. Pure hexanol is fed to the column to extract the acetic acid. Okay, so another stream containing pure hexanol go in the extraction process as well. The water rich stream leaving the vessel is 99.5% water and the balance acetic acid. The hexanol rich extract from the vessel is fed to a distillation column. So from the extraction process, we go to the second process, which is the distillation process. The composition of distillate is 96% acetic acid and balance is hexanol. The bottom stream containing 97.2% hexanol and recovers 95% of the hexanol fed to the liquid extraction vessel. Okay, so this is another equation. Recover 95% of the hexanol fed to the liquid extraction vessel. So here we have the amount of acetic acid that had been introduced into the extraction system, extraction process, and 95% will be recovered. The hexanol will be recovered in the liquid. Okay, so this. Okay, so calculate the percentage of acetic acid in the process feed that is recovered in the distillate stream. Okay, so there are a lot of information here. Again, the first step is to read and try to extract and try to understand the whole picture on how to solve this problem. And the way to do it is to draw the block diagram so that we can get more understanding and clearer view about what is going on. So it consists of two processes. One is extraction and the other one is distillation, in which M1 is the feed and M2 is the hexanol, pure hexanol. M1 is the feed that contain 18% of acetic acid and 82% of water. Then after the extraction process, the bottom one contain a lot of water, only just a very small fraction of acetic acid, and the other stream will go to distillation that contain hexanol and acetic acid. We have no idea what is the fraction here, and then the distillation will distillate it into two stream. The distillation that contain rich in acetic acid will be on top with M5, and the bottom one, M6, will contain hexane. And this hexane is equals to 95% of the total hexane in M2. So this is the another equation. So in order for us to solve this problem, let us watch the video by the University of Colorado here, where this video we show the same example and how to do the calculation for it. So let's first watch together, and you can get more details of the video.
The purpose of this screencast is to show an example of setting up and solving material balances on a multi-unit system where we have a liquid-liquid extraction column in series with a distillation column. We'll touch on the ideas of fully labeling a process diagram, degrees of freedom, and setting up a system of material balances. In this problem, we have acetic acid and water that's being fed to the process. These two species are difficult to separate by distillation, so the purpose of the liquid-liquid extraction column is to transfer acetic acid from water into hexanol. And the acetic acid-hexanol mixture is then fed to the distillation column, where the acetic acid can be separated. The schematic of this process is shown below. However, we don't have any information that's provided in the problem labeled on the flowchart. At this point, it's important to take a moment to look at what's been given in the problem statement and see how we can apply this information to fully label the process diagram below. After reading the problem statement, it's clear that we don't have any flow rates that have been given. It's important that the total flow rate of every stream is either known or labeled with an unknown variable, so I'm going to go through the process of labeling each of the 6 streams in this process. All of the compositions that have been given are in weight percent. So I've given a variable of M1 through M6 to represent the mass flow rate of the 6 streams in the process. The easiest way to fully label the diagram is to go line by line through the problem statement and apply the information that's been given to the appropriate stream. For example, we have some information about the feed to the liquid-liquid extraction column. We know that we have a mixture of 18 weight percent acetic acid and the balanced water that's being fed to the extraction vessel. So we can apply that information to stream 1. Here we're given that the mass fraction of acetic acid is 0.18, and if the balance is water, we know that the mass fractions need to sum up to 1, so the mass fraction of water must be 0.82. The problem states that the other feed to the liquid-liquid extraction column is pure hexanol, which corresponds to stream 2. The water-rich stream that's leaving the extraction column is 99.5 weight percent water. Keep in mind it's the acetic acid and hexanol that's going to the distillation column. So this is the stream M4 that's not being fed to the distillation column. In this stream, the mass fraction of water is 0.995, and we know that hexanol and water don't mix. So without hexanol in the stream, the mass fraction of acetic acid must be 0.005 so that the mass fractions sum to 1. The hexanol-rich extract leaving the extraction column is fed to the distillation column. Here it does not provide any information about the composition, so we're going to have to label M3 with an unknown composition variable to represent the mass fraction of hexanol and acetic acid. So here I've labeled the mass fraction of hexanol arbitrarily with the variable x. And again, we know there's no water in this stream, so the mass fraction of acetic acid must be 1 minus x. We do have some information about the composition of both the distillate and the bottom stream leaving the distillation column. We know the composition of the distillate is 96 weight percent acetic acid and the balance hexanol. The bottom stream is 97.2 weight percent hexanol and the balance acetic acid. So that information has been applied to M5 and M6 respectively. We have one more piece of information that's been given to us. Problem states that 95% of the hexanol that's fed to the extraction vessel is recovered in the bottom stream. So that can't be applied directly to the information on any particular stream, but we can represent that information mathematically. 95% of the feed should be 0.95 times M2, and that's equal to the flow rate of the hexanol in the bottom stream, which is 0.972 times M6. So at this point we've accounted for all the information that's been provided in the problem statement. Let's take a look at what's being asked in the problem. We need to calculate the percentage of acetic acid in the process feed that's recovered in the distillate. So we want to know how much of the acetic acid going in is being recovered in the distillate here. Before we start writing and solving equations kind of haphazardly, the next thing to do is do a degree of freedom analysis on every system in this particular process. That'll illustrate to us the easiest way to proceed to calculate what's being asked for. Alright, I've scrolled down a little bit to make some room to do the degrees of freedom analysis on this process. We can apply this analysis to every system in the process. In this case we have 3. So we have the liquid-liquid extraction column, we have the distillation column, and we have the overall process. So the feed to the process and the outputs to the process. So we'll go through these one by one to see where we should start setting up mass balances to solve for what's asked for. So let's start with the liquid-liquid extraction column and count up how many unknowns we have. We have M1, M2, M3, the composition variable x, as well as M4. So we have 5 unknown. We can relate these unknowns with material balances. However, the balances need to be independent, and the number of independent mass balances that we can write will always be equal to the number of species that we have. We have A, we have W, water, and we also have hexanol. So we have 3 species in this particular system. We can write 3 species balances that are independent. Keep in mind we can also write a total balance, however, the total balance is going to be the sum of each species balance, so it is not independent from the 3 species balances. So in this case we have 3 independent mass balances that we can write. We also don't have any other information that relates any of the variables in the extraction column. So, without any other information, 5 minus 3 gives us 2 degrees of freedom. We're short on the equations that describe these variables. Hopefully we can find another system where we have more information specified. Next, let's take a look at the distillation column. Again, we need to know how many unknowns we have. So the feed to the distillation column is M3, and again we have the unknown composition variable x. We also have an unknown M5 and an unknown M6, so in this case we have 4 total unknowns. The number of material balances that we have, or independent material balances, is equal to the number of species. However, in this case we only have 2. We have hexanol and we have acetic acid. Water is not being introduced to the distillation column, so in this case we only have 2 independent balances that we can write. And again, in this case, we don't have any other information that's relating the unknowns. So without any further information, we also have 2 degrees of freedom for the distillation column. So let's take a look at the overall system. The system boundaries for the 2 unit operations here, the extraction column and the distillation column, are pretty straightforward. For the overall system, we're concerned with the inputs and the outputs to the process. So to help us visualize the system boundary for the overall process, I'm going to draw a line that intersects the inputs and the outputs to the system. So when we do a degrees of freedom analysis on the overall system, we are only concerned with the streams that are intersecting the system boundary for the overall process. That includes the 2 inputs to the extraction column, the 2 outputs to the distillation column, but it also includes one of the outputs from the extraction column that does not go into the distillation column. So let's see what variables we have. We have M1 going into the extraction column, we have M2, we have M4 leaving the extraction column. We're not worried about M3 because that's internal to the system. We are concerned with M5 and M6. So it looks like we have 5 unknowns. For the overall system, we have 3 species in acetic acid, water, and hexanol, so we have 3 independent balances we can write. We also have another piece of information that relates the unknowns in another equation different from a mass balance. We were given some information about how much of the hexanol going in ends up in the bottom stream. So we have one other equation that we can use. So we're left with 1 degree of freedom. However, if you look at the flowchart, you'll notice that there is not one flow rate that's specified. We always need to have at least one flow rate specified. In other words, we need a basis. So if we assume a basis in one of the streams in the overall process, we can go from 1 degree of freedom down to 0 and start solving for the unknowns. Which flow rate we assume for a basis is arbitrary, and I'm going to use M2 and assume that we have 100. So you can see that if we assume a basis of 100 for M2, that essentially eliminates one of the unknowns, and therefore we'll have 1 less degree of freedom and give us a 0 degree of freedom system. I've simplified our flowchart here so we can start calculating unknowns related to the overall system. Keep in mind what we're trying to calculate. We want to know what the recovery of acetic acid is in the distillate, which is here, relative to what goes into the process, which is here. So minimally we need to calculate values for M1 and M5. We can do that using mass balances in the other equation that's been given to us that relates the amount of hexanol in the feed to that in the bottom stream. So we wrote that mathematically using this equation. Since we assumed a basis of 100 for M2, we can quickly calculate M6. So substituting in 100 for M2 gives M6 is equal to 97.7. And here I'm not assigning units with these flow rates. The units are really arbitrary if we're calculating a percentage recovery or a ratio of any 2 flow rates. If we want to calculate values for M1 and M5, we're going to need to relate them by material balances. We can write a material balances on the overall mass. We can also write a species balance for the 3 species that we have. We'll assume that we're operating at steady state, so all of our material balances are going to have the form of in equals out. If we apply that equation to the total balance, then we have M1 plus M2, which we assumed is 100, is equal to M4 plus M5 plus M6. If we want to write the balance on acetic acid, on the inlet side, we only have acetic acid in one of the inlets to the extraction column. So we have a mass fraction of 0.18 times the total flow rate of M1, and that's equal to the sum of the acetic acid in the 3 outlet streams. I'll quickly write the balances for both water and hexanol as well. I also substituted the value for M6 that we calculated to the acetic acid balance. With all the material balances written out, we can come up with a strategy that is easiest to solve for the remaining unknowns. So looking at this system of equations, we can see that our H balance here just has one unknown in M5, so we can calculate that first. And with M5 calculated, we can solve any 2 of the 3 remaining balances simultaneously. So I'll pick the acetic acid and the water balance. So solving the H balance first to solve for M5 gives a value of M5 is equal to 125. Once we know M5, we can calculate M1 and M4 by solving the acetic acid and the water balance simultaneously. So I won't go through that algebra, but we'll just provide the answers. With all of our remaining unknowns calculated from the mass balances, we can finally calculate what we ultimately want, which is the recovery of acetic acid in the distillate. So mathematically, we can write that the percent recovery is equal to the concentration in the distillate times the flow rate, which was M5, divided by what went into the feed. And the composition that was given originally was 0.18, and our flow rate for M1 is 697.9. So if we calculate that out, the recovery is 0.956, or in percentile, we have 95.6% of the acetic acid is recovered in the distillate.
Okay, so that's another example of how to solve the problem when it's come to the multiple processes with mass balance. So beside that, the normal multiple processes may also involve a few situation where it will also have the recycle, bypass, or purge stream, in which we go one by one recycle stream. That means that a process from here will have to go back to the stream that in the previous process. And for bypass, some of the stream will bypass any particular process. And for purge system, stream bleed off to remove an accumulation of unwanted materials and so on. So this is purge that might also normally happen in any particular processes. So what will happen to the material balance if situations such as the recycle, bypass, or purge stream happen? So that's why we can try to do example 10.3, and this one is to do some processes that involve recycle without any chemical reactions. Okay, a distillation column separate 10,000 kgs of 50% benzene and 50% toluene. The product D recovered from the condenser at the top of the column containing 95% benzene. Okay, so all the information has been given here. We have the feed that contain 50% benzene and another 50% of toluene to the distillation column. At the vapor entering the condenser from the top column is 8,000 kg per hour. A portion of the product from the condenser is turned back. Okay, so after this vapor go to the condenser, a recycle stream happen, where after the condenser, a portion of the product from the condenser is returned to the column as reflux, and the rest is withdrawn for the LCS. So this is withdraw, this is going back to the distillation column. Assume that the composition of the stream at the top of the column B and the product withdrawn D and reflux R are identical because the V stream is condensed completely. Find the ratio. Okay, the question, find the ratio of the amount reflux R to the product withdrawn D. So we want to find the ratio of R to D. So how to solve this? Of course, the first thing that you need to do is to do the DOF first. After you draw the diagram, but in this kind of like a bit more complicated situation, most probably the question will provide you with the diagram, so you will not going to be confused with the stream that go in and go on and what are the processes that may involve. However, in some situation, if the question does not provide you any diagram, you need to draw it yourself. Okay, so in this case, it's already been provided. The first thing is to perform the DOF. You need to perform the DEF of the overall of the distillation column, the condenser, and in fact here also this is we call it is also a separation process, although it doesn't have any box. Yeah, so this is the first step that you need to do in order for you to know where to start. But for in this example, I'm not going to do any D or F. I'm just going to start from the overall balance here. So the overall balance consisted of only F, W, and also D. So all of this in the boundary of the system will not be considered. For the condenser, let's just see. For the condenser, the balance will consist of V and also D and also R. Okay, R. So that's where it's very important for us to identify the boundary of the system so that we can do the calculation. So let's start by doing the overall balance first. Overall process. So for overall process, the general balance or the overall balance, the total balance is F equals to D plus W. Again, F equals to D plus W. This is for the overall process because we don't consider what inside of the boundary here. So we have F as 10,000 and we don't have any value of D and W. So this is considered as equation 1. Okay, for the I'm going to go for the benzene because we have two components. One is benzene and one is toluene. So we are going to go for the benzene BZ balance. So for the overall benzene balance, we have 10,000 times 0.5 equals to D times 0.95 plus W times 0.04. So after the we do the sum calculation, this is 5,000, 0.95 D plus 0.04 W. So at the end, we just going to simplify as D. 5,000 minus 0.04 W divide by 0.95. So this equation 2. So what we can do is to put 2 into equation 1. So 10,000 equals to D, which is here 5,000 minus 0.04 W divided by 0.95 plus W here. So we can do the calculation. This is very easy. .95 W. So at the end, you are going to get W equals to 4945 kg per hour. Again, don't forget about the unit. if the unit in kg per hour, you need to put it there. But if the question asks you to change from kg per hour to other unit, you need to do the conversion. And then after we got W, we can also obtain D, which is 10,000 minus 4945 is equals to 5,055 kg per hour. Okay, so we got W, we got D, the value. Now the second thing, because we want to know what is the ratio of R and per D, right? The ratio, we already got D value, we got everything, but we have to find R value now. So we go to the second balance, focusing on the condenser. So I'm just going to divide it here, sorry. This is for the condenser. You don't have to panic if you see there is a bypass or purge, because the way to solve it is more or less is just the same. You just need to do step by step. Okay, for the condenser is V equals to R plus D. Okay, so V is 8,000. We want to find R plus D. We got 5,055. So R is equals to 2945 kg per hour. Okay, so the question want to know the ratio of R over D. So 2945 divide by 5055. So the ratio will be 0.58. Okay, so well, actually the way to solve it is similar like the other multiple processes mass balance. You just need to focus one process to another process, and maybe in the overall process before you can solve the question. Okay, so this is the last example, example 10.4, bypass calculation. In the feedstock preparation section of plant manufacturing natural gasoline in isopentene. Okay, isopentene natural gasoline removed from butane free gasoline. So we have we have butane free gasoline. So the process is steady state and no reaction occur. What fraction of the butane free gasoline is passed through the isopentene tower? Okay, so we want to know what is the, we have all the information given in the diagram here. We have isopentene from the butane free. So we want to know what is X, because what is the fraction of butane free gasoline is passed through the isopentene. So again, for this one, the first step is to do DOF. However, for this case, I'm not going to do DOF. I'm just going to start with the overall balance. Overall, so for overall balance, the general balance will be F equals to S plus P. Okay, so F equals to S plus P. Okay, so we are not considering what inside of the system, we're just going to consider the overall process where only F, S and P involved. Okay, for this one, the component balance, and you are referring to the NC5, okay, 100 0.8 equals to S, which is 0 plus P 0.9. Okay, for this one, because S is times 0, so we're going to get P equals to 88.9 kg. Again, go back to here. This is 100 equals to S plus 88.9. So S is equals to 11.1 kg. So now we have the S and P. Okay, and then after that we are going to the other balance, which is, okay, so we have the balance, we have here S equals to 1.1 kg, and P we have 88.9. okay, so now we are focusing on the balance of the isopentane tower here. So what go in? X equals to S plus Y. So now the question asks us, what is Y? How much is Y? Okay, so now we are going to the tower balance, in which for the general balance F equals to X equals to S plus Y. For this one, we don't know what is X, we know what is S plus Y. So this is equation 1. And then for the component balance, NC5, we are going for NC5, X 0.8 equals to 11.1 times 0 plus Y 100%. So this is 1. So at the end we are going to get 0.8x equals to Y. This is equation 2. So 2 into 1, we are going to get X equals to 11.1 plus 0.8x. So X will be 55.5 kg. Okay, so this is the answer for X, but if you want to find also Y, we can find it, but the question asks for X actually, but let's just find Y. 55.5 minus 11.1, so Y equals to 44.4 kg. And the question asks, what is the fraction of gasoline that pass through the isotone? We want to know what is the fraction of X compared to F, the fraction of X. So the F fraction, X per F, so X is 55.5 and for feed is 100, so the fraction is 0.56. So this is the final answer for question in for example 10.4. So I really hope that you are going to do all the exercises here, and in the same time please refer to the textbook and other reference book in order to get more understanding about the example given about the multiple processes mass balance, because for this type of problem, what you need to do is to solve it step by step in order for you to get a final answer, and hopefully you will be able to apply it later. So I think that's the end of the lecture for today about the mass balance of the multiple processes, and we are going to do exercise during the tutorial. Thank you for watching. Bye.